All right, higher derivatives. Higher derivatives. What are we talking about? We are talking about second order, third order, fourth order, and by order I mean the power of the differential function. So let's just see it. You have z subscript x. You have partial z over partial x, z subscript y, partial z over partial y, z subscript xx is also partial square x over partial x square, and then z subscript y is partial square z over partial y square, z subscript yx. The y comes before x, so it's going to be, this is the first differential, this is the second differential. So the first differential is this, the z over dy. The second differential is d over dx. This is also partial square z over dx dy, while z subscript xy with the first differential, partial z over partial x, and then you have y d over dy equals to d square z over dy dx. Example, so these are the higher different, so these these and these, like four of them are higher differentials. These and these are higher differentials. Why? Because the power of the differential is more than one. We are using this square here, so this order, these two order two. Yes, these two order two. I hope I'm not mistaken. There's order and degree. If I do mistake, then I'll correct myself along the way. So tan, yes, tan inverse of z is equal to tan inverse of y over x. Prove that partial square z over partial x square plus partial square z over partial y square is equal to 0. Solution: z is equal to tan inverse of y over x. Z is equal to tan inverse of y over x. Differentiate the z over dx. The z over dx is equal to 1 over 1 plus y over x square. I am praying you were taught this in MTH 106 so that it doesn't confuse you. But let me just explain it here. When you're giving y is equal to tan inverse of x dy over dx, differentiating this with respect to tan inverse is 1 over 1 plus x square, yeah, times differentiation of this with respect to x is 1. If you're giving y is equal to tan inverse of x over a, dy over dx is going to be equal to 1 over 1 plus x over a square times derivation of this with respect to x is 1 over a. So you're going to have a square. Okay, let me know. Just know these how it is. What if it's sine inverse of x? Let's say y is equal to sine inverse of x. How do we do it? The y over dx is equal to 1 over root 1 minus x square. If it's y is equal to cos inverse of x, don't worry, if I'm also wrong, if I'll correct myself later. The y over dx is equal to minus 1 over root 1 minus x square. So these are things you actually need to carry in your head. So let me separate this so that it doesn't confuse me when I'm making the explanation. This is alright. So now back to this. Tan inverse of y over x is 1 over 1 plus this square times the relation of this with respect to x. X is down, so we use quotients here. So you have v, the u dx is 0 minus u, the v dx is 1 all over v square, which is x square. This is what you have. So this is 0, this is minus y over x square. This is 1 over 1 plus y square over x square. Because I guess this is the first time we are working with this, so let me explain. Okay, that's why I explained it. So after now, most of this long working, you will see it again. The square partial z over partial x is equals to 1 over LCM. I did the LCM of this, that will be x square. So the LCM is x square. This is 1 over 1. 1 into x squared is x squared. X squared times 1 is x squared plus x squared to x squared is 1. 1 times y squared is y squared. So you have 1 over x squared plus y squared all over x squared times minus y over x squared. The next thing is open it up. You know how it's supposed to be 1 over 1 divided by x squared plus y squared over x squared. When you change this to multiplication, you're going to inverse this. That's why I did here. So it's now 1 over 1 times the inverse of this x squared over x squared plus y squared, they call times minus y over x squared. Straight up, I just said x squared will cancel out x squared. 1 times minus y will give you minus 1. 1 times x squared plus y squared times 1 will give you x squared plus y squared. So that's differentiation of z with respect to x. Now the square z over the x square, the square z over the x square is also quotient, so it's v du dx minus u dv dx all over v square. So we have v, differentiation of this with respect to x is 0 minus u, which is minus y. Differentiation of this with respect to x is 2x all over v square, x square plus y square, everything raised to power 2. When you open the bracket, this is out is 0, minus and minus is plus, so you have plus y times 2xy is 2xy all over everything square. So this is the square z over the x square. Alright, so the same thing for here we are differentiating tan inverse of y over x with respect to y this time. So differentiation of z equal to tan inverse of y over x will be 1 over 1 plus y over x square times y is on top, y is the numerator, so you can just differentiate it there. If you open this, you're having y times 1 over x. 1 over x is a constant, so differentiation of y is 1, so you have 1 times 1 over x, so it's 1 over x. Also for the other one too, you're having y times 1 over x. Y here is a constant. We are differentiating 1 over x. 1 over x, you can call it x to the power minus 1. So when you want to differentiate, it's going to be minus 1x times minus 1 times x to the power minus 1, which is minus x to the power minus 2. When you multiply by y, you have minus y x to the power minus 2. When you change to fraction form, it's going to be minus y all over x squared. So depending on how you want to differentiate it, the one that will be easier to remember and the one that will be quicker for you. Alright, so we differentiate this tan inverse, you get this. Differentiate this with respect to y, you have 1 over x. The same thing, you open it. Here now, I didn't have to show them collecting item and everything, so I just went straight up to it. X squared all over x squared plus y squared times 1 over x. X will cancel the square here, so the z over dy is equal to the z over dy is equal to x over x squared plus y squared. Now the square z over the y square is, you use quotient rules to get it. You're differentiating this with respect to y again. So you have v, differentiation of x with respect to y is 0 minus u. Differentiation of this with respect to y, this is 0, this is 2y all over v square. That's everything square here. This is 0, this is minus 2xy all over everything square. Yes, and then so now you're asked to prove that the square z over the x square plus the square z over the x dy square is equal to 0. So the square z over the x square is 2xy all over x square plus y square, everything square. And now the square z over the y square is minus 2y all over x square plus y square, everything square. Open a bracket, you have minus, so they are the same. When you minus them is 0, so we've actually proven that it is 0. Alright, so be sure to go through it. Okay, that'll be it.